Alright, hi everybody. My name is Tristan Hagerman. I am a distant student for the class. Today I'll be covering the topic of astrometric aberration as described by Professor Frueh in the most recent lecture. So, in opposition to chromatic aberration, which is due to the bending of different frequencies of light inside of a lens, astrometric aberration is related to the difference between the observed position of an object and its true position at the same time based on its velocity and distance to the observer. Now, for astronomers, this is relevant because of the vast distances to distant stars, which can take thousands, if not maybe even millions of light years to reach the observer. So those positions from what we see currently and where the stars actually are now is significantly different. And because of this, as described in the end of the notes, when observing distant stars, you have to take into account also the velocity of the observer on Earth. So there is an annual correction and a daily correction due to aberration that need to be applied to your star observations. And this is taken into account with equations 4.58 to 4.64. However, when viewing satellites in orbit, the velocity relative to the observer is more relevant than the distance, and therefore the time that it takes for the light to reach the observer, which is a bit more in line with a term called light time correction, but that doesn't take into account the relative velocity of the motion of the observer. So, to simplify my coding example, I've used the example of an object passing overhead as a satellite for somebody on the equator if the satellite's motion is also along the equator, so that the two motions are in the same plane, so that the angular difference between the position that is seen and the position that the spacecraft actually has is only in one direction, a circular direction. Also, I used overhead so that the lensing of the atmosphere isn't taken into account. So to achieve this, I used the Earth's mean radius for an observer at sea level, probably at the equator. I used the angular velocity of the Earth because that's going to be taken into account later when we calculate the difference between the angular velocities of a satellite and the observer. The Earth's gravitational parameter, the mean moon distance, just as a cap for this range of what I calculate, and then c for the speed of light. So to create a series of potential satellite positions, I swept our satellite variable from a low Earth orbit to the mean moon radius. I also assumed circular orbits for this, so I could do a simple calculation for the velocity of the spacecraft using the square root of mu divided by the satellite radius, the orbiting radius. So I said that from the observer to the satellite, the distance is rsat minus r-Earth, the radius from the center of the Earth to the observer. And I said that the time for the light to reach the observer is the distance that I just calculated times or divided by c. Then I calculated the circular velocity of the spacecraft, and then I calculated the radial velocity of the not radial angular velocity, sorry, of the spacecraft. But I also subtracted the angular velocity of the observer because that's going to be taken into account. Then I said the angle relative to the center of the Earth is equal to that angular velocity of the spacecraft times the time it takes for the observer to reach the light to reach the observer. And then the actual angle between being directly overhead at the zenith, what the actual observer sees, and where the spacecraft position actually is at that time, there's a simple trig calculation using the triangles formed between the observer and the spacecraft and the center of the Earth and the spacecraft. So if you plot all of this between low Earth orbit and moon orbit, you can see it's somewhat like logarithmic here at the end, as one would assume, and then it's fairly linear elsewhere. I noticed that there was a point in which it goes from being a positive difference, where the spacecraft is further ahead than the observer sees, and where the spacecraft is behind where the observer sees. And if you look, that point is at about 42,000 kilometers, which falls in line with the distance to a geosynchronous orbit, which is where over the observer at zenith, that spacecraft doesn't appear to be moving. So it makes sense that beyond this point, the spacecraft would have a negative velocity angularly to the observer, as if it would appear if it were pregressing in space, and therefore the light-based aberration, the light time correction, would be in a negative angle instead of a positive angle. So this has been my coding example.